talking about these changes in the adaptive versus the innate immune system sort of reminded me of Dr. Valtralongo's research, who I interviewed a few months ago, and he was talking about how this prolonged fasting in mice, which is about 48 hours, or translates to like 4 days in humans, which is quite a long fast, but was able to just very robustly clear away damaged cells, presumably senescent cells as well, also caused cellular death, but followed by a massive and robust increase in stem cell proliferation, sort of replenishing the population. But what was so interesting was that it seemed to, at least in aging mice, if you did this in aged mice, it normalized the difference between the innate and the adaptive. So like you were mentioning, the adaptive immune system declines with age. But this fasting sort of like replenished somehow, I guess, the adaptive, maybe some of the stem cells.
In the bone marrow, yeah.
Yeah, and so you maybe have more of a 50-50 ratio like you do when you're younger.
Right.
So what would be interesting is if you like somehow did that experiment where you did some fasting and, sort of regenerated that adaptive immune arm, I guess, of the immune system, and then like gave some chemical to cause cellular senescence and see if there's any change in...
Well, a lot of Valter's work also has to do with the side effects of chemotherapy, right? So he was able to show that with this intermittent short-term fasting, even in humans, he could not only improve the efficacy of chemotherapy, but prevent some of the side effects.
Right.
So we've shown very recently using mice, a transgenic mouse model, that some of the so-called genotoxic chemotherapies, the chemotherapies that damage DNA, definitely causes senescence. And if we eliminate those senescent cells in our transgenic mouse model, we can eliminate several of the side effects, several of the bad side effects of chemotherapy. So one possibility is that what the fasting does is it might eliminate senescent cells. More likely, what it might do, we think, is dampen mTOR activity. So just to remind you, mTOR is a kinase which is highly conserved from yeast all the way to humans. And it's a nutrient and growth factor sensing kinase. So high nutrients, high TOR activity. And what has been shown in yeast and worms and flies and mice is that if you dampen, you can't get rid of TOR activity, you need it for life, but if you dampen TOR activity, either genetically or with the drug rapamycin, which is known to target one arm of the TOR pathway, you can extend lifespan. And what we showed recently is that what rapamycin does, or dampening TOR activity does, is it also suppresses primarily the inflammatory arm of the secretory phenotype of senescent cells. So it could be that fasting and rapamycin and the secretory phenotype of senescent cells all come together around the TOR pathway, and that it's really TOR activity that's driving both the aging phenotypes, the side effects of chemotherapy, and may partly explain the benefits of the short-term fasting that Valter is a proponent of.
Interesting. So if it's dampening the secretion of these cytokines from the senescent cells, but it's not actually getting rid of the senescent cells, or...
It's not, so far as, well, we've shown that either genetically or pharmacologically with drugs like rapamycin suppresses the secretion of senescent cells, but it doesn't kill them. So unlike some of these other drugs, that these so-called senolytic drugs that actually kill senescent cells, the mTOR drugs, the mTOR dampening drugs, suppress the ability of senescent cells to secrete. And the effects are last longer than the application of the drug, in the sense that we know that part of that secretory, pro-inflammatory secretory phenotype is due to a feedback loop. And what dampening mTOR does is it breaks the loop. And the loop takes time to reestablish. So even after you withdraw the drug, you still get suppression until eventually the loop reestablishes and then the cell starts secreting again. So you might think that if you were to fast for 4 days, every few weeks, you might have more benefit, certainly more benefit than taking a drug like rapamycin, which has side effects.
Right. Because you're not only, when you're fasting, you're also clearing away the damaged cells, in theory. I mean, we don't know how much of that's occurring in humans yet,
yes,
but we do know
in
animals,
mice, that's right.
that happens. And then the other thing, when it kind of goes back to the mitochondria-induced senescence that we talked about a minute ago, is that we know that fasting increases NAD levels, and so the NAD plus NADH ratio. And that sort of is very interesting because this mitochondrial-induced damage, I think, has something to do with declining NADs.
It does, actually. So that's what we've shown, is that this mitochondrial dysfunction-induced senescence, we call it mitochondrial dysfunction-associated senescence, or MIDAS. So we call it the MIDAS phenotype. Really has to do with this altered NAD-NADH ratio, and that's one of the drivers. Interestingly, so when you change that ratio, you activate a kinase called AMP kinase. AMP kinase is a major regulator of P53. P53 is a major regulator of both senescence and apoptosis. So that could be the link of why, in Valter's paradigm, you get reduced inflammation. That could be due to suppressing the secretory phenotype, but also increased apoptosis because you now have activated P53.
Right, exactly.
Yeah.
So I just got sort of lost in the question I was going to ask you, but okay.
No, one other thing I was going to I don't know if you're going to ask this question, but it's worth discussing, is the stem cell, the regenerative process that Valter has seen. So we also know that the secretions of senescent cells can have very profound effects on stem cell proliferation and function. So it could also be that by dampening the secretory phenotype of senescent cells, you now release those stem cells from the suppression that was due to those secretory phenotypes, and therefore allow them now to do what they do best, which is to proliferate and regenerate a tissue.